Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all of you. Welcome to the Antenna How Does It Work program. This program is organized by the Microwave Communication and Information System Engineering Research Group, Kuliah of Engineering IIUM, and ECESA IIUM. The program is sponsored by IEEE Region 10 Educational Activities, IEEE Malaysia Antennas Propagation, AP MTT EMC Joint Chapter, and IEEE Pre-University STEM Portal. Model 1. Introduction to Antenna and State of the Art. Now, let us look into this figure first. Can you spot the wires on top of the cars? Sometimes these wires are placed in front of the car, and sometimes it is placed at the back of the car. Have you ever wondered what these are for? Next, the wires on top of mobile phones. Ever wondered what the wires are for? Is it for design purpose, or is it there for any specific reason? How about the two vertical wires on top of the old television in this figure? Some are also placed on rooftops. Sometimes it looks like an array of wires, and sometimes it looks like a dish. Do you have any idea what these are? Yes, probably most of you know that it is an antenna. So, what is it and how does it work? From the Webster Dictionary, antenna is defined as a usually metallic device as a rod or wire for radiating or receiving radio waves. From the IEEE standard definition of terms for antennas, they define antenna as a means for radiating or receiving radio waves. So, in other words, antenna is the transitional structure between free space and a guiding device. To understand this better, let us look into this picture. The signal will travel from the generator or the source into the transmission line, then entering the transition region, which is the antenna, and finally into the free space. And at the reception mode, which is the receiver, the free space wavelength will then enter into the antenna, which is the transition region, and then goes into the transmission line and finally reach to the receiver. So basically, you will have one transmitting antenna and another receiving antenna. A transmitting antenna will transform the electric currents into radio waves, while the receiving antenna will transform back the electromagnetic field into electric current. Let us look into the relationship between wavelength and frequency. Wavelength is denoted as lambda, and it is measured in meters. Lambda is equal to the division between speed of light and the frequency, which is measured in hertz. As we increase the frequency, the wavelength or lambda will decrease. For example, if your frequency is at 10 to the power of 4, the proximal scale of your wavelength or your lambda is as big as a tall building here. But as you increase your frequency, say 10 to the power of 12, your wavelength will become more smaller, and the approximate scale of wavelength is around a needle point, the size of a needle point. This is a summary table of a frequency band and frequency range. It started with extremely low frequency ELF with a frequency of less than 3 GHz, followed by VLF from 3 up until 30 kHz, and then we have LF, MF, HF, VHF, UHF, SHF, and finally EHF, which is extra high frequency, with a frequency range of 30 up until 300 GHz. Next, let us look into the types of antennas available. These are wire antennas. Wire antennas are some of the oldest, simplest, cheapest, and most versatile for many applications. You can see them almost everywhere, on cars, buildings, ships, aircraft, and even spacecraft. There are actually various shapes of wire antennas available, such as the straight wire dipole, helix, and also loops. Next, we have aperture antennas. These antennas are used for high-frequency applications such as aircraft and spacecraft application because they are conveniently flush-mounted on skin of the aircraft or spacecraft. They can also be covered with a dielectric material to protect them from hazardous conditions. Some of the examples of aperture antennas are rectangular waveguide, pyramidal horn, and conical horn. Next is the microstrip antennas. These antennas are used for government and commercial application. They consist of metallic patch on a grounded substrate. The metallic patch can take many different configurations. Sometimes it can be rectangular, sometimes triangle, or even circular. The advantages of microstrip antennas are that they are low profile, conformable to planar and non-planar surfaces. They are simple and cheaper to fabricate using modern printed circuit technology compared to other antennas. These antennas are used for high-performance aircraft, spacecraft, satellites, cars, and even mobile phones. Next, we have array antennas. Arrays may be used for applications that require radiation characteristics that may not be achievable by a single element. Arrays are actually an aggregate of radiating elements in an electrical and geometrical arrangement, which will result in the desired radiation just like we want. Finally, we have reflector antennas. These antennas are in popular demand due to the need to communicate over great distances. A reflector antenna is very sophisticated because it can transmit and receive signals that had to travel millions of miles. There are actually many more antennas that are available in the market, which are made in various shapes and sizes. In summary, an ideal antenna is one that will radiate all the power delivered to it from the transmitter in a desired direction. Various types of antennas are available, and each type can take different forms in order to achieve the desired radiation characteristic.